So our research question was birthed from this idea of, at first we thought we were going to have access to a lot of legacy thin sections from a core warehouse to where we wouldn't have plug data available. We thought, can a detailed analysis of the porosity from a thin section potentially characterize the three-dimensional pore networks, more importantly, the three-dimensional porosity and permeability, to help make CO2 storage decisions? And if so, what of these pore network characteristics would be most effective for a CO2 storage field? So I've been happy to work with my advisor, Dr. Zane Job, and my committees rounded out by Dr. Rick Sarg and Dr. Miles Henderson. So just to give an idea of where we're heading before we look at the methodology, what we're trying to do is we're trying to develop a shape quantification methodology that can pair with an SEM scan. From this, we've seen that within the San Andreas, pore shape, size, and abundance is variable between and within facies, confirming things that we already know. What was interesting is that there was no correlation to being able to try and predict what plug porosity would be from our two-dimensional scans. We've also found that as average pore size increases, our permeability increases, also confirming things that we already know. We're also able to quantify things that would be tortuosity metrics. As pore complexity increases, our permeability decreases, and as our pore connectivity reduction increases, permeability decreases. Just a couple high-level definitions of things that we'll be talking about a lot during the talk before we get into it. First of all would be an SEM, or a scanning electron microscope. This is an electron microscope that produces images and compositions of a sample by bombarding it with electrons. So you slide your thin section into this microscope, it sends an electron down in and it tells you what it's made of. Also, Python is a growing coding language that's becoming ever more intertwined with the geoscience field. And this is just a general purpose coding language often used with data science techniques. And I'd like to just take a minute to talk about, I feel like it's been a privilege. When I first came back to school, I had no idea what data science was or had any real intention of trying to pursue it. But I think fortunately, I was able to work with an advisor and eventually a project that required a lot of it. And I think that from this project has given me a perspective on what type of a balance can be found between a geoscientist and a data scientist. So when I first wrote this code in Python to try and scan the thin section, it took 14 days to run. And I was panicking. I was like, this is not going to work. It's too long. No one's ever going to want to wait. I'm not going to even be able to graduate. We then consulted with a true computer scientist. He was able to make the code more efficient, and it now runs in 3 hours, which really helped the efficacy of the project. However, I think that as technology continues to increase, it's beneficial for geologists to be somewhat fluent in some of these data science languages and to be able to communicate our goals efficiently to the computer scientists to help optimize the code. So I think that there's room for both people in this space as it continues to grow. And big thanks to Ross Meyer for saving my butt. So now let's jump into the study area. We're interested in how some of these depleted oil and gas reservoirs, specifically San Andreas reservoirs in the Permian Basin, could be potential candidates for sequestration locations. You see we're here in the Permian Basin on the left, and again, our study area is shown by the red dot. When we blow up and move over to the image on the right, we have a structure map of the top San Andreas. We're focused on the Goldsmith field, and more importantly, the Goldsmith Landreth San Andreas unit outlined by the white polygon. As you can see, we're kind of in between a saddle of 2 high points here on this carbonate structure. There'll be 2 wells that we'll be working with, the 126R and the 190. These both have cores, thin sections, and plugs associated with them. So here's our 2 studied wells, the 126R and the 190. The major San Andreas here is broken into the upper and lower San Andreas. These are the G4 and G8 cycles from the BEG or Charlie Caron's classification scheme. But just to keep it simple, we'll call them the upper and lower San Andreas. These 2 wells have cored different intervals of our section. The 126R has tagged the base of the Grayberg through the upper San Andreas and down into the lower San Andreas. The 190 has cored the lower portion of the lower San Andres. And by combining these two together, we have a full look at our full strat section. So from these two cores, we had 23 thin sections and 6 different facies. The facies were derived from core descriptions by Stout and Abdullayev in 2012. We selected 11 of these 23 thin sections for the study. The foundation for the choices of why we chose 11 out of 23, number one is we wanted to try to encompass the range of facies that were available in the field. We wanted to try and have multiple thin sections per facies to see how they would plot, group, and or separate. And we also wanted to stay within our time and economic limits of something like a master's project. You can see that there's a lot of grain supported facies ranging from mud-rich packstones to true grainstones. There was the waxstone facies. We had one thin section from that and it just wouldn't stitch when it came out of the SEM. And if there's any more questions on the technicalities behind the image stitching, I'd be happy to expand on that later in the talk. So now that we have our data set, I just want to kind of give you a roadmap of our methodology for the steps we took to try and come to the correlations that we did. We take our thin section, we put it in the SEM where we can get a very detailed mineral map of the thin section. From there, we can derive our porosity map and get each pore to be an individual polygon. From there, we run our original script on our shape analysis for each and every pore in the thin section. Finally, we correlate that to the 3-dimensional porosity and permeability found at the core plug at the corresponding depth. So you can see here, we're taking an existing thin section and just mounting it right to the stage of the SEM, taped it down, and you can also see that we can run multiple at a time. So we never tried to fit more than 2 at a time, but if you had smaller thin sections, you could. We gave the thin sections a quick polish. They were carbon coated to help with the efficiency of the SEM. On average, it was about a 5-hour scan time. This can range from under 3 hours to up to 7 hours, depending on what your scan area is and how complex your sample is. And our resolution is 1.5 microns per pixel. So any pore that's 1.5 microns or larger, we can detect. Anything smaller may be beneath the limit of detection. So as we go through the next steps, I'm going to use a frame of reference to kind of show what the SEM is trying to do and how we feel like it's giving us a detailed boundary of our polygons. So we start with a thin section. Here's our example. The black outline shows the area that the SEM will eventually scan. And this smaller red window will be the example shown in the SEM software. The SEM wants to send light down into the sample, and it will return different grayscales of different compositions. There's multiple minerals across the thin section, but we're just going to look at the main ones that we can see here with the naked eye. You can see here in the true black, we have pore. In the dark gray, we have dolomite. In the light gray, we have calcite. These differences are because as the electron comes down into the sample, it's then warped or pulled by the weight or size of the nucleus. As these nucleuses are different sizes, it will affect the angle at which the backscattered electron comes out, showing different colors of grayscale. Here's the completed BSE map that the SEM has done over this thin section. Again, you can see the detail that we were just working in the small window. Here's the entirety of the scan. So just with our naked eye, we can see these changes in BSE. The SEM can see much finer changes in the BSE of these throughout the image, excuse me. Where it sees these changes, it will mark it with a red plus sign, as you can see, that it wants to go in and investigate the mineralogy of this location. At each one of these red plus signs, it'll send an electron beam in, it'll knock out an electron from the inner shell. An electron from the outer shell will jump down and take its place, and it will emit a characteristic X-ray that is unique to each element on the periodic table. So as it shoots a location, you'll get an emission of energy that can measure, and you can say, this is the element that's at this location, and you can group them to find your minerals. Each one of these red X's will come and be accompanied by a spectra, an EDS spectra. And you can use your domain knowledge to group these elements to make minerals. You can see in plot A, we have a peak at oxygen and a peak at silicon. We can group these together as quartz. Then the software will then propagate this interpretation across the thin section and say anything that has a similar type of distribution will also be quartz. Similarly, here see in B, dolomite with carbon, oxygen, magnesium, and calcium. We call that dolomite. You continue to interpret your EDS spectra until the entirety of your thin section is then mapped. So here's the final result of this thin section. I really like this one just because you can see the real beautiful fuselinated molds in here, and the pink is calcite, the blue is dolomite. There's a little bit of anhydrite, some quartz, and then the pore is shown in white. Detailed mineral map. Not only is the SEM going to be good at telling us a detailed boundary of where our minerals start and end, but also where our rock ends and where our pore begins. And we want to bring this porosity map into Python and kind of recreate it in our own terms to where we can create a polygon and save it to be analyzed later. So what we do is we export the pixel map from our SEM analysis and bring it into Python. And what we're given is just a small dot. We have a location and a label of saying this position of the pixel is at XY and its label is pore or its label is calcite. We bring those in and we want to fill that pixel in the area that it represents, and we do that with a pixel patch, when everything turns out to be a very small square. After we create a pixel patch around each pixel, we then group. Still too better?
It might not be on. Is it live on?
We back?
Yeah, we're back.
Okay. It must have been right on the holster there. Thank you. Thanks for that. So I'm not sure how much we missed there with the mic being off. But so we've created our detailed mineralogy map with the SEM. We brought it in, and now we want to recreate a detailed boundary of where that pore is. First, by creating a pixel patch, grouping pixels from the same pore together, and then drawing a detailed polygon around it. So here's the output figure. And again, we're just now focused just on the pores. Everything else is turned off. And again, this was the window that we had been looking at. So here's an example of some results of just 6 different thin sections. The ones that we were looking at are here on the bottom. Each have a BSE image, a mineralogy, and then a pore map. Now, I think this, you can do some quick back of the napkin math and get your area percent porosity. But I think the thing that's most interesting was it's a battery issue. I'll just try and talk louder if it goes out again. But the number of pores that you find in each of these thin sections is fascinating to me. If you were to ask me before I did this, I'd say there's like 1,000 in there, maybe 2,000. Some of these have almost 200,000 pores in there. And I think it details the fact that if you were to want to measure and analyze each one of these, it might be not worth the human time. But now we're going to ask the computer to do it for us. So now that we have our pore maps and our polygons saved for each pore in each thin section, we're now going to run it through our pore shape analysis. So we have 17 shape measurements from 4 shape descriptors. You can see here on the right, we have an example. So the blue line is the pore body. The black line is the convex hull, which is the tightest fitting polygon that would encompass all the points of the pore. The equivalent area circle is shown in gray, which would be if your pore is 100 pixels, your circle would be 100 pixels, but fit into a perfect circle. You also have a minimum bounding rectangle, which can give you the length, width, and long axis orientation of your pore. So this was iterated for each pore in the thin section, and over 1 million were done just for this study. What we found was that area, convex area, perimeter, complexity, and equivalent circular diameter were the most important metrics that we had measured. So just to jump into some of these ones that we're going to be talking about later in the talk, as you can imagine, area is just the number of pixels that can be found within that shape, or in this case, within the pore. The perimeter is the boundary length of that shape. The convex hull, again, is the smallest polygon that encloses all the points in that shape. The convex area then is the area of that convex hull. The complexity of the shape is the ratio of the shape perimeter to the shape area. So you can see here, this is an example of a highly complex pore. There's a lot of pore wall and not a lot of pore area. This who has a lot of pore area in comparison to the amount of pore perimeter. The next thing we wanted to do was document what rock the pore was hosted in and what potential connectivity it had to other pores. So this combines the benefits of what we're getting from the SEM, both the resolution of the measurement and also the mineralogy. So again, it will document the pores hosted to the rock. You can see that when you zoom into any one of these small pores, this is an actual example from one of the thin sections. Everything, I gave this presentation as somebody says, it reminds me of Minesweeper. Everything breaks down to just their small squares. So you can see here we have an example pore shown in the middle, shown in white. There are 7 pixels that surround it that are calcite, 1 that's anhydrite, and 2 other that are pores. So the pore lining minerals of this pore would be 70% anhydrite, 70% calcite, 10% anhydrite, and 20% pore conductivity. However, we've come to think of these pore contacts as the reduction in pore conductivity. A pore would prefer to have a boundary of a long axis. When it's contacted on these corners, we see that as a reduction in pore conductivity. So we'll see this manifests itself in the permeability measurements as we move forward. Now back to the core plugs. Again, this is an example of one of our cores. It has plugs taken every foot, so quite dense. Each of them have porosity, permeability, oil, and water saturation taken on each plug. The shape metrics, pore lining minerals, and pore conductivity are going to be correlated to the plug data at that corresponding depth. Here's just the core plug data visualized, permeability on the Y and log scale with the plug porosity on the X. We can see that it's a cloud and the R squared is 0.36. If we subset the 11 thin sections that we use for this study, they're shown on the right with permeability on the Y and plug porosity on the X, with our trend staying the same, however, with our R squared diminishing due to reduction in data points. So we had our data and we thought we were ready to rock. And when we started to plot these, we started to realize that there was a couple outliers with how much porosity was being shown in comparison to the plug porosity. What we come to find out is that these thin sections that had the highest amount of anhydrite also had the highest amount of SEM porosity in relation to plug porosity. So you can see in 4143 and 4303, they have high amounts of anhydrite, and their SEM porosity is almost twice that of the plug porosity. As we dove into the images, and also by consulting with subject matter experts, we believe that some of these pores are artificially made by the thin section creation and polishing process. The polishing is done with fresh water and glycol along with the abrasion of the polish. We think that these pores are not analogous to what we're seeing in the subsurface, but artificially made as we try and prepare the thin section for SEM. You can see here some of these striations from abrasion. Then the next question was how are we going to deal with this potential problem? We kind of had not planned for this, but since our pore lining minerals were already defined for each pore, we were able to subset the data. Okay, we can emit and sort the data set. We can omit pores that have a pore lining of a certain amount. So we started obviously at 0%, our way to what was the cutoff for where we believed pores would be artificial or where they would be true. And what we decided is to use a guide as what the relationship is from our plug porosity to our SEM porosity to define where that cutoff should be. So here's the original data with the plug porosity on the Y and the SEM porosity on the X. And here's our 2 outlier values, far away from the line, along with the plug porosity being consistently more than the SEM porosity. After we had omitted our anhydrite porosity with greater than 20% lining, both of those points got back. They started to behave a little bit better on the correct side of the line, fitting in the tighter cloud. So now this is what I think of as a baseline. We have a base amount of porosity measured from the thin section, how is that going to correlate to permeability? And now does these shape analysis of the pore, do the characters of the pore, can they help us predict permeability and porosity better than just the rough porosity will? So permeability to SEM 0.41, porosity to SEM porosity 0.23. We'll see if we can beat these things with our shape analysis. And here's the methodology behind how we're going to analyze this data. So pores in each thin section were grouped into two groups. One, all of the pores in the thin section. The other one are macropores. These are characterized as pores with greater than 10 micron equivalent circular diameter. So we had spoke before, we have a pore, say the area is 10 microns. We give it a perfect circle with the same area and then what that diameter is. So if it's larger than 10, it's considered a macropore. The statistics taken on each of these parameters will be the mean or the average, the median, and the geometric mean. Oftentimes, the mean is beneficial when you have a unimodally or an evenly distributed data set. The median and geometric mean are used when your data is skewed or not uniformly distributed. Oftentimes in geologic data, and in this case here, we have data that's not normally distributed, as you see that is heavily skewed. So we'll take each of those three measurements on each parameter. Then what we'll do is we'll hold permeability or porosity static on the y-axis, and we'll iterate through all our parameters on the x-axis to see which one gives us the best R-squared. So from that pairings, from our 17 shape parameters, through our 5 pore lining minerals, our 3 different statistics, and our 2 different pore groups. Again, we were trying to find correlations that beat 0.41 for our permeability. I think this is a good time to remind that we found no correlations that correlated to the plug porosity. Nothing beat what the SEM could predict at 0.23. However, with our permeability, just the area, as the mean area of our macropores increased, it correlated with our permeability at 0.71. Honorable mention, the convex area at 0.69, and the rest of these are just artifacts of the pore getting larger, whether that be equivalent circular diameter, major and minor length, and the convex perimeter. On the other hand, analogs for tortuosity were also found to have correlations with our permeability. The first one was our complexity metric at 0.61. And then just making the cut was our connectivity reduction. So you can see here, we have a panel of our mean area macropores. As permeability is shown on the Y with the log axis, as our mean area macropores increase, our permeability increases with an R-squared of 0.71. Here we have both cores, the upper core and lower core, broken out to show how these trends will hold with fewer data points. Again, almost a mirror image of our mean convex area to the permeability, followed by the broken out by the upper and lower core measurements. So here's our 2 tortuosity analogs. First is our complexity, again with our example that we saw before, but as the median pore complexity increases, our permeability decreases with a factor of 0.61, and again, respectively broken out to the upper and lower core, with both of the trends holding the same, but our R-squared diminishing due to reduced data points. Now down to our macropore connectivity reduction. We can see that as the connectivity reduction increases, our permeability decreases, holding true with the fact that as the pores become more tortuous, it's harder to move fluid through. The next steps that we want to take in the study, and we're currently working on this now, is to try and define our pore throats throughout the entirety of our pores from our pore shapes. You can see on this image on the left, we have a really complex pore running through the middle of our thin section, where it'll neck down and open back up multiple times to where we wouldn't want to find just one minimum enclosure for a shape, where some shapes may require to have 10 measurements of pore throats and some may require only 1. So what the watershed algorithm does is it takes measurements around all of the boundaries and measures where the furthest points are from all the different boundaries. And it treats these as basins. You can see that where there are separations from these basins or little islands, it would then quantify that as a pore throat. This was first done by Rabbani et al. In 2014. He did it in a different depositional environment, and he did it in MATLAB. So we think that we can atone for our needs. So here's an example of how it would work. We would feed it a pore. It would then take the distance measurements from all the boundaries to show where the deepest points are within the structure. It would then interpret different basins, so to speak, and break this shape into different segments. From there, we can pull the shape out or pull these segment boundaries out, take it back into our pixel space and measure the length of the line. You can see that these two sub-basins are playing nice. However, the reason it's still in our working phase is that we're still having trouble for some of these lines to come out straight, not jogged, and touch both sides. However, we're still able to measure what the pore throat length would be. This would be repeatable, between different data sets. And we'd be able to obtain these measurements for tens of thousands of pores in the thin sections instead of just a handful. So again, this is just a methodology development. We know that we have a low number of data points to qualify something as statistically significant with our R² value. We wanted to have the application for this study would be the CO2 injectability. So as the permeability would be analogous to CO2 injection in depleted reservoirs with legacy data sets, scan the thin sections and be able to break the tidal fields. We feel like this methodology has the potential to extend to other environments or to serve other purposes, whether that were to be identifying fracture density and orientation in some thin sections. You could find the size distribution and shape distribution of grains for other depositional environments, and of course, porosity for other depositional environments. So in conclusion, again, we tried to do a development of the shape quantification paired with the SEM. Pore shape, size, and abundance is variable between and within facies. We saw no improvement to correlation and plug porosity. As average pore size increases, permeability increases. As pore complexity increases, permeability decreases. And as pore connectivity reduction increases, permeability decreases. It's been a lot of work, and I wouldn't have been able to get all this done without a help from a lot of folks. First is the data science group, Data Science Earth Resources, led by Dr. Zane Job, Matt Bauer, and Dr. Thomas Martin. I'd like to say thank you to the University of Texas Permian Basin, Miles Henderson and Bob Trentham, for allowing us to kind of play in their sandbox and allowing us to work with one of their data sets. Also, Bruker Nano Analytics and Mines Automated Mineralogy Lab for helping kind of create the project and teaching me how to scan thin sections and deal with the data. So be happy to take any questions you have at this time. Thank you. Yes, sir.
As it relates to, this is kind of, you're doing this for carbon sequestration, correct?
Yeah.
So I guess with the analysis, how does that correlate to the ability to sequester carbon in this? Or is that still included in this phase?
Yeah, so we see that permeability could be an analog to what the CO2 injectability could be at the wellhead. And a lot of these projects, we've come to understand the economics will be based on how quickly and how much injectivity you could have in a short period of time to keep your economics up. So we think that if we could find a stack of rock that has high permeability, regardless of resource in place, and you could compare and contrast analysis like this between multiple fields, maybe that could be a tiebreaker on understanding what your injectivity would be at in one field or the other. Does that answer your question?
Yeah.
Yes, sir.
Was there any difference between what you saw on the lower St. Andreas versus the upper, since you've got that unconformity separating the two?
Yes, there definitely was. And there's also a diagenetic difference
Yeah, that's what I was looking at.
between the two. So you can see here that we only have a few sections from the upper San Andreas and some from the lower, but you can almost see the increase in limestone as you go down and the increase in anhydrite as you go up. And from that, we consistently see, so the purple star and the black diamonds are from the lower San Andreas, along with the red squares. But you can see that the lower San Andreas are plotting lowest on the permeability. And then your upper sections, especially from the upper San Andreas, are plotting highest on your permeability as well. You're welcome. Yes, sir.
I'm curious about the three-dimensionality of your thin section. Your resolution is 1.5 microns. Standard thin section is 30 microns. So you're looking at a whole big pile of stuff that could have 30 or there. What's the depth of investigation of TPS? Are you looking at just the carbon film? And if so, how does this go in? Or is it actually sampling something that's below that carbon film surface?
Yeah, that's a great question. So we use 20 kiloelectron volts. So this is just an estimation, but 2.5 microns, roughly a depth that we're going in. So this might be more than what you bargained for a response, but there's a little bit of a double-edged sword when you get your deeper investigation, is that you're also getting mineral mixing in your response, because that cloud is going out wider in the X and Y direction, or Latin long direction, I guess. So sometimes if you're trying to shoot a dolomite, you might have a signal that's leaking over into your neighboring calcite, and it complicates the response that you get. But to answer your question, we use 20 kiloelectron volts with a depth of 2.4 microns. Yes, ma'am.
I have a question about how you model the pores and the pore connectivity.
Mm-hmm.
And with the diagonal set up with each other, that was those were connected pores and those kind of connectivity. But if the blocks are right next to each other, wouldn't that just be a bigger pore?
Yes. Yes. So so how the SEM identifies it is that if two pixels are sharing a long axis, then it's the same pore. If they're sharing a corner contact, then they're not the same pore. So that's the way we're able to identify if it has a pore neighbor or not. And the way that we've kind of framed it is that it's obviously going to be easier to flow through a long axis contact than through a corner contact. So we assume that this is a reduction in its pore connectivity to where it would prefer to be connected through a long axis, but we can still document when it's contacted on the corner. And we see that that would be harder to move fluid through.
Well, and so let's move block 5 where block 4 is right now. Is that just a larger example for them? Can you ever model pore connectivity along one of the sport?
So if there was a white, if there was a pixel, a pore pixel here in number 3, it would just be lumped in as the same pore. Yeah.
Thanks.
Yep. Well, that's a complicated. It's taken me a few times before I've able to been efficient at delivering it, and I think it still could use some refining. So.
No, I think it was just I was wondering how that translates, and then jump to Python and modeling.
Yeah.
We've always got.
Thank you. Yes, sir.
So most of your discussion of anhydrite, what I interpreted as a sample preparation is problems.
Yeah.
Quality of data.
Yeah.
Were there enough good images that involved anhydrite that you thought were real, where you can say anything about what is the interplay of anhydrite with pre-existing pore structures, or what's, where's the fill in the genetic history, or is there anything trustworthy you can do to see that hydride?
That's a good question. From the conversations that I had when we embarked on this problem, that we assumed that if we see anhydrite, it should be completely filling the pore. And if we see voids within that, we assume that it had been plucked out. One thing that I did prepare was what would the correlation be if we didn't touch the anhydrite problem? And this might be really small, but we still get the same correlation. We still get the same idea that as average pore size increases, our permeability increases. So it doesn't affect our outcome as much. I think it may highlight just another applicability to the methodology to say, if you run into situations to where you want to omit certain types of pores, you have the functionality to do that. But I don't know if I have the technical expertise to answer the remainder of your question.
Well, go ahead. Go ahead. I think you were gonna address John's question.
No.
Oh, okay. I was just gonna circle back on your comment about that muddier sample not stitching correctly.
Yeah.
You can explain what that process is, why it works.
Yeah. So you can see that when the SEM does this, it does it in fields of view. Everything is just a small rectangle. And then you ask the software to try and stitch them back together. So I tried to use red arrows to show there's like these vertical and horizontal streaks that run through the image to where it looks like it's off, it's blurred. And what happens is if you export this without stitching the image, now all of a sudden it's tripling or doubling your pore numbers. Or if a pore is supposed to be a perfect circle and it's not stitched correctly, it'll be offset. So now the shape and count of that pore is incorrect. So I just felt like it would have been not valid data without the ability to stitch. And the explanation I got from the software company was that in that sample, so this isn't that sample. That sample, there was not enough heterogeneity to be able to identify and pick up anchor points where it needed to lock in.
And how did you QC or identify that that wasn't happening correctly? How did you know?
Yeah, so you run the stitching, and then for that one, it was quite apparent that it was not doing it correctly. However, for samples like this, I would identify areas where I could tell that it wasn't stitched and kind of remember them. I'd have it stitch, export the picture, like the image, and then put it on a big screen and then go into my areas that I knew were bad to see if it had corrected them or not. So each one went through a stitching and a QC process of kind of flying around the image to make sure that everything looked correct.
If it wasn't stitched properly, would you see like a line where it was just not matching up, or would it be more?
No, it was definitely like you could see a line that would kind of persevere for a while. And then sometimes you would also see like just one block that just couldn't find it. It's like musical chairs almost. Like everything was fitting together and that one just like, well, I just don't have any room anymore. So apparently it's a technology that is still growing, the image stitching. So fortunately, we only had one that had that problem. And as from speaking with the SEM company, it seemed like that's a problem that they're trying to address, because what you don't do then have them all come back and say, well, we just can't stitch these. So, yeah.
Okay, so I'll pre-apologize if you covered this. I'm supposed to include. But on your KV plot that you showed, was that for the entire data set? And did you do it not show that you actually grouped them by faces and looked at your KV relationship there? And if so, did it improve?
So you're talking about the R squared correlation?
Yeah.
So we know that so I've been referencing this paper quite a bit for the thesis. So this gentleman in 2006 did a very detailed description of pore type and what that improvement for R squared of predicting permeability could be. So I think we know that if we identify what the pore types are within the facies, that should give us an indication of what its permeability should be. However, for this study, that was a little bit outside of the scope. I mean, we obviously want to be able to plot and keep the facies in mind. I mean, the reason that the porosity and permeability relationship is because there's different pore types. So we wanted to keep these different facies by plotting to see how they group together. But mainly what we did is we just took what was the porosity, shape, and size distribution and how it correlated to the permeability independently of the pore type. Yep.
Any other questions? Let's go ahead and give a round of applause.